So, hey, that was it. So sorry for all these announcements, but I think it's part of moving from in-person to online course. So the lecture today is about a highlight of like unimodal representation, and also start understanding like the core concept, or at least some of the key concepts to neural network that are going to be very important for this. So let me start with unimodal representation, and I have a little bit of a bias sometimes because I've been myself doing a lot of research in computer vision back in the days. So so maybe that's why I put it on the top. But yeah, so the one of the interesting aspects of unimodal is to take all these images, which is relatively high dimension. You have like 640 by 480. That's back in the days 20 years ago. Now you have 4K resolution. So, and you also have multiple what's called channels, RGB, our example, red, green, and blue. And with this, what do you want to do with an image? What the simplest thing you would like to do with this will be to, for example, recognize a dog. Is it a dog or not? That's a classic problem with that will help us probably on back in the YouTube recognizing all of the cats and dogs that are shown there. So so what is the representation for an image? And this is probably for some of you, you already done computer vision and you're like, oh, I know how an image is represented. But some of you may just have done maybe more from natural language processing or other. So I just want to give you the basics so that we can build from that. So an image is mostly a matrix. That is what I would call almost the raw representation, uncompressed version. Yes, there are compressed versions of images. There's some interesting work also in representation learning directly uncompressed representation. But for now, uncompressed images mostly is a matrix. And the X and the Y will mostly be the position in the image of the pixel. And if it's a grayscale image, it's a 2D matrix. And if it is a colored image, it's usually a 3D matrix where the third dimension will be the Z kind of dimension will be these different colors. So mostly what it is three 2D matrices stacked together. That's what what this is about. All of them are stacked together. And so when you do image classification, the simplest one will be take this 3D matrix and just go directly to your neural network or classifiers and get the output. But this is a matrix, and most classifiers expect more of a 2D vector. Very long 2D vector possibly, but they like 2D vectors. So what is the simplest way to go from 2D image back in the days to to a vector that can be used by a typical classifier, the simple feed-forward neural network, multi-layer perceptron, or maybe even like old school style support vector machines, which I still like quite a bit for certain tasks. Yeah, so the idea is to just stack, and you just end up concatenating all of these together. That's just the simplest way to take an image and make it as an input vector for a classifier. And so when you do binary classification, then the idea here is that you will simply go from this binary answer sorry, not to the binary answer, but the input, you want to be able to get the binary output like 0 or 1, is it a dog? There are different type of classification. This is just to be sure we all have the same naming convention. There's what's called multi-class classification. Multi-class means that In this case, it's either a dog or a cat or a dog. It's kind of, it's either of them. It cannot be both of them. It's one or the other or the other. So object classification is an example of what is often seen as multi-class. But sometimes it's multi-label. The same image maybe have more than one object in it, and in which case you would like not only to be able to see it as like, is it a dog, a cat, a dog, but in fact you would like it to know for each of the categories what's called class labels, or a label class will be to give you, is it a dog or cat or dog? Yeah. So this is just basics to get everybody on the same. And this is, it can be regression, so we can do it not only for one, but like for discrete, but you can also do continuous, like age, height, weight, and distance. Okay, this is Computer 101, just the basics. We'll start often from something, as most of the time we'll start for something like this. When I will later on tell you, oh, we use a CNN, and you ask yourself, what is that input X? There's a very good chance the input X is just a vector or a 3D matrix like this. How is it for language? How do you take language like this and just make it as a vector? What is the right way to do, or what is, no, let's not go on right or wrong, but what was the popular way to do it until recently? And even now we're still using at the basic, the input, quite similar representation. So the most basic way of representing language, and by language I mean either a sentence, a word, a sentence, or paragraph. The representations are quite similar in this. And by the way, there's two terminology that we'll sometimes use in this class. There's written language and there's spoken language. So written language, something you type with a keyboard, or these days with a phone, or spoken language, which would be also, we could call transcriptions. In both cases, the representation will be often, if I want to represent one word, like humorous, and let's say I want to know from this word, what is the sentiment for it? Then what is the sentiment? Is it positive or negative? I'm starting very simple right now. One word, how will you represent one word? And the answer to that is one-hot encoding. This is still, when you look these up to like 3 years ago, 2 years ago, when we were, maybe even less than that, when we were encoding with word2vec or love, and we'll discuss these about representation, the input will often be something very similar to this, a one-hot encoded. What it means is you have this very long vector, very, very long, so long you cannot even see my my hand. So very long vector, and then what is that length? The length of it is the dictionary. Dictionary will be either dictionary, and most of the time will be based on the training set. Will be like, look at all possible words in my training set, and for each of these possible words, that becomes one entry in my dictionary. That is what we will call the dictionary, the language dictionary. You could use a dictionary that from another corpus. You could imagine a larger one, but usually often people will do. One thing also some people will do that they don't tell you, but they often do, is they will have a threshold, like they will say, any words that do not appear at least 10 times will not be part of my dictionary. And it will be in that other category called others or junk or any like so if your dictionary was like 1,000, you will have 1,001 for all of these other words that you put there. That's one way to do this. So this is your one-hot vector encoding, and this you could imagine then use this and use nice maximum entropy model. Maximum entropy model, we'll discuss a little bit them later, or conditional random fields are all very well suited for that representation. It's very nicely approach. So and using this, you can do quite a bit. You can do word level classification for every possible word. You could imagine having that vector and know, is it a positive or negative? You could do what's called a name entity recognition. Recognize which words are about a person or an entity, or maybe a city, a town. Then the part of speech tagging will be another example of task you will do with. So which part of the sentence, which words are nouns, verbs, adjectives. So this is what's called word level classification. That's a term that I will use. But sometimes you want to do it at the document level or paragraph level. And so how do you encode at the paragraph level? I'm a little bit too fast with my clicker, but it's also a one-hot encoding. But there you could call it what some people will call a bag of words, where mostly what you do is for you have still the same long dictionary, and you just encode every words in that dictionary, every words in that document or in that paragraph. And you just set it to 1 when the word happens and 0 otherwise. That's the simplest one. You could also make it as the number of instances in that document. So you just do a +1 every time the word is there. And sometime, or we'll do maybe a normalization after that. So this is, and then you can do the same task, sentiment analysis, and you can do that for written language, or you could also do it like if you have the transcript of dialogue, you could also do the same as well. So this is the idea for language. And I would also like to talk about acoustic modality. So you're listening to someone, you have this audio. What is the most basic or the raw representation of audio? Think about it for a second. What is that representation? I see it in blue here. It looks like it's 2D, but really audio at its basic is a 1D. It's a very long vector. We here it's showing the amplitude of it, but yeah, but the idea here is that the audio at its basic is a very long vector. So in a sense, you could use that long vector and directly try to predict, for example, what is the spoken word right now? What is, so I could imagine like slicing this and take that vector, segment it maybe by hand, or have someone automatically segmenting maybe with silence if it's a, let's say, a digit, speaking digit, like one digit after another where there's a pause in between. And so you could imagine some of the old style speech recognition doing it by pause for segmentation, and just take this and take a vector. And then you could imagine just going and take that vector with some padding, because not all of them will be the same length. But this is not how we do it in reality, but this is something you could do or someone could do, but don't do it. And the sampling rate is just how many of these samples within 1 second. So if you have 1 second of, if we have 1 second of audio, how long is going to be the vector representing that 1 second? Okay, and 8 kilohertz mostly mean it's 8,000. This vector is will be 8,000. 96 mostly mean there will be 96 numbers to represent 1 second. So you can see, I forgot the exact one, but when you talk about HD, and sometimes it's just like the sampling rate is just 8K is, if I remember correctly, related also to the old phone, digital phone, or some of the phone technology was within that. Yeah, and so the depth is like for each of these, if you have a vector of 8,000, each of those numbers, will it be 8? Will it be 8-bit, 16-bit, or 24 bits? And it's all about discretization, like how fine-grained do you want your discretization? Because at the end of the day, like you could almost imagine, like I speak, and usually you often will go from nothing to the max, and there will be often a cutoff. And so this is how much energy, speech energy, you could imagine it that way. And then 8-bit mostly say, how big are going to be your bins? 16 says how it will be a lot more fine-grained, and 24-bit. And then the 8 kilohertz and 96 kilohertz is really about then the temporal bins of this. So it's the same signal, it's just how big the bins on top of this. So this is the idea for like the most simplest one. And then how do you represent this for spoken words or for any processing? There is usually, in a perfect world, you will have like a nice set of segmented units, and then you will use that. In reality, you don't have that in most cases. So what people will do is slice the signal, and they're like, you could call them windows, time windows that you will slice, and then you will repeat those time windows. And so, and often these numbers are like, if you want to start with some numbers, these are a good place to start. If you talk with your TA or you talk with me, we can give you more details on like what specifically for your data set, but these are usually a good place to start, where the time window, let's say 20 milliseconds. So you could imagine 20 millisecond, 1/20, that will, 20 millisecond, you can transfer that in hertz as well, by simply dividing 1/20 milliseconds. But the offset will usually be something like the half of the time window. You want some overlap into that. But this is too simple, and this is in fact not how human even are perceiving audio. And there's been wonderful work, and that work is definitely more than in the last 5 years. This is work of more than 30+ years on analyzing acoustic signals. And the key insight is in the ear also. People don't seem to represent things just like as a long vector. They seem to be doing it more in a frequency domain. So what they will do is take this window of audio, and from this window of audio, say in that small window, how much of very low frequency do I hear? How much very high frequency do I get? I should be careful when these lectures get recorded. So very high, very low. And so what you get here, I forgot to put the y-axis here. These are the frequency from very low frequency to very high frequency. And these will be in kilohertz also, but it's confusing because sampling rate is at kilohertz, but here the frequency will also be in kilohertz, but they're different things. Sampling rate is how big my bins. You could say each of those lines in this original blue lines, what are they? Like how often do I have them? Here, it's like once I take a bunch of these samples and do a fast Fourier transform and like get the frequencies, how much, and here the spectrogram I'm showing here, is you could see how much of each of those frequencies do I get in that. And the idea is to move this along. So here what I show is one slice, and these are mostly a set of numbers at that time, at this point in time. And then I will do plus 10 millisecond, and then I will get another of these, and I will plot it here. Another of these, and I will plot it here. Every 10 millisecond, I will plot it. And finally, I can get that full spectrogram. So the full spectrogram here is over a long period of time. Now, do you use the whole spectrogram as your input? Probably not. Probably you will want some way of segmenting. So again, you could have a new window that you move over time. Maybe you will use a larger time window that you will move over time to look at, let's say you want to detect like, I don't know, we want to detect maybe laughter as a, let's say as one example. So how would you detect laughter in this case? So that's an example of what you could do with this. In this case, let's say you have already segmented the words, and you can take that and do a recognizer. Back in the day, you would use an HMM for that. Now you'll definitely use neural networks. So this is computer vision 101, or I don't know what's before 101, 100, language 100, and like unimodal 100. It's very the basic, like what is it? So in any future model I show, like probably 95% of the time, the input for computer vision, for language, or for acoustic will be one of these three things. They will be very low level. An example for language, it will probably bag of words is really what I will start with as the input. But sometimes some people, and maybe myself, will be a little bit lazy and don't even give you this input, and will directly give you like the process input, which will be run it through a neural network like word2vec and give you a new vector, maybe of length 300. But what they didn't tell you is before that there was this vector, and really rarely do people take the time to show you that basic representation. They're like, oh, this isn't any textbook, but this is a class, so I'm here to give you the basic textbook version of that. Okay, so this is the basic representation, and you can do the acoustic, you can get word, and you can do emotion recognition and all of this, and often spectrogram. There's been work now these days trying to use directly the digital raw input for audio, but most of them still use spectrogram as input for that. I want to give a little bit more on other unimodal representations. I will not go in as much details, but I really, if you have to read one more paper this week, pick one of these and go and read about these other representations, because we are focusing the course on language, vision, and acoustic, primary language and vision, but I really want you to explore eventually, or at least read about other modalities, because there's a lot of other modalities out there. An example here is, that sounds like a Minority Report, yeah, Minority Report, or these glove kind of things. The idea is that you can recognize that I'm touching an object. So this is, the idea is the glove will have an array of sensors on it, and then how much pressure is on that sensor will suddenly be given to you. So if I get this array of sensors, I can then suddenly put them in almost of a 2D grid. And because you see, once you start seeing CNN here, that should give you a hint that these people decided to take what is probably more than 2D, because if you move things like this sensor is in fact very close to each other. So anyway, but yeah, in this case, they look at it as a 2D sensor, which is quite interesting. And then you can use things that we'll discuss in the coming week, something like a CNN or convolutional neural network. So this is one example of a sensor. What's interesting about it, there's quite a bit of redundancy here. It's a little bit like an image in that sense, like two very close sensors will be very similar to each other. This is different from language, because in language, one word can be quite different from the other. They will be related, there may be grammar and other things that relate them, but in this case, we'll have a lot of redundancy. And so you could imagine the kind of representation should take advantage of that redundancy. And CNN is one known one to be useful for that. I want to give you other type of sensors. In fact, even that like sensor that I showed you, often another way to represent it is over time, because it's not only an image, but it's almost like a video, because each of these sensors will get more or less pressure over time. So often you will get representations, and in a sense, it does look a little bit like you would see an audio signal, and so you could imagine, because it's an audio signal, probably the first thing that comes to mind is like, hey, maybe I want to move it to the frequency domain. That's a good idea, and I would strongly suggest it as maybe a first step in that direction. And so when you see these, that's also why I want you to think, although I may not always talk about all those other representations, you should be able to make the link between them and be able to go and see how to, like in this case, it is not directly an acoustic signal, but it does show a little bit of repetitions. And so maybe if I want to take advantage of that, maybe frequency domain will be good. Maybe for some others it will not, because what we need is maybe more of a template matching, which a convolution network is mostly a template matching, and we'll talk more on this. But so that's another thing you can do. And an arm or a robot arm is in fact as part of a lot of these. When you see a robot arm and slowly and going and grabbing something, what you don't see, or you know only if you start studying robotics, but there's a constant loop. Some people often call the control loop, like that will be there to allow you to move and adjust yourself as you move closer. And that loop will use this kind of input signal from all of the actuator, all the motors, and will allow you to change or adjust. You could imagine, I know we're not robots, but you do, or for people who have a driving license, you do a little bit the same. I mean, you always, maybe you would like to predict ahead of time or anticipate things, but usually you do your, in real time will change all of your angles. So you only have a very simpler problem when we do the driving, in the sense of simpler, not that self-driving is simple, it's not. But what I mean here is that there's only two angles here. There's also the acceleration of the gas. And as you know really well, there's a lot of the extra sensors important there. So, but I wanted to give an example, another examples here. Another thing is we think of language, for example, and if I give you a table like this, back in the days, although there had been some attempt with table to text, but recently what we see is take advantage of the positioning of the text. It's not just text, because you could imagine going ahead and just parsing it and just keeping it and going one line at a time. But there is a structure in it, and there is proximity, and I may want to take advantage of that proximity in a table. And so how do I take advantage of that proximity in a table to do something like, in this case, it's table to text generation, but I will leave it to you to think of other applications as well. So I want you to think, one that I didn't put there, but is quite related, is sketch recognition, because often people will sketch, and here you will maybe with OCR, optical character recognition, we will recognize what has been written. But there's a lot of other things, like a box that you highlight a thing with a box, you start drawing some object, and you want to be able to take advantage of that. And so you could imagine looking at it as a 2D table, or looking at it as an image, pixel, or looking at it as a vector, because all of it has temporal information when you do sketches. So these are different representation. I also want to bring graphs. I think graphs are very important, and they've been studied for a while, but like, for example, in economic and biomedical. But more recently, we see them coming out from social network research, internet networks, all of these. You see graph, and I put graphs here. There's also another part of it, which is knowledge graphs that is important, which you can see in natural language processing. And there, but let me talk about, like, for example, social network, where you have everyone on Facebook or everyone in a specific network or sub-network, and who is related with who. And related is really the key here. A graph at its basic, what is a graph at its most basic, is often represented with a node or a set of nodes and edges. That's like the most basic representation. Now, this can be enhanced, like the nodes themselves could have information associated with it. And the edges themselves could be quantized, or they could be association associated with it. So, for example, you could have nodes that are every possible entities in your knowledge base. So, like Pittsburgh and hockey and penguins. So you have 3 entities. All of them have nodes associated with them, and then the edges will be some kind of relationship with this. So knowledge base, you will have a team or hockey team, or I have to think of all the relationship, but the edges will be those relationship between entities. In the social network would be relationship between users. So so it's really interesting to use this kind of knowledge, and quite challenging, because neural networks that we'll use in many of these by default really love 2D vectors. They love that, or sometimes 1D vectors, not 2D vectors. 1D vectors, I may have said 2D vectors in the past, 1D vector, and also look at 2D matrices. But when it's a graph, how do you represent that with neural representation, neural architecture? It's very interesting to look at that. I just put one example in this at the bottom of this slide, but this is just to look as a teaser in that direction. And sometimes your data has a kind of an extra structure. It's not just an image, but you have a set of images. Maybe because all of these images are all from the same person. Maybe this person when they were very young, or under different lighting conditions. And so this is really example. The example here is for face recognition. Or there's some sensors. I mean, what we see these days with self-driving cars, you can see these sensors, and what they will give you, some of these sensors will be a point cloud. So point cloud could be because you have a sensor that gives you depth and is just scanning around. And so you could see it as a 2D image. But also you have sometimes sensors that are like 3D sensors, 3D scanning sensors that will take an object and acquire it by looking around. You could also imagine just a 2D, one sensor and then moving the object. But anyway, at the end of the day, what you get in all of these is a set. You had a set of points, or what you usually call a point clouds, or a set of image, and you want to be able to take advantage of that. And so maybe you want to do anomaly detection, or you want to look at it even in a generation sense. So I wanted to give you a few examples of other unimodal representations, and I invite you to look at these papers. You're here to learn, so reading is great. So I will go a very, very short amount of time on machine learning, that like very quick there's just a basic naming conventions. It's just that if I don't do this now and I use these terms later, we may get a little bit lost. So at least now we're all on the same place. And I will start talking about neural representation and neural networks soon after that. So basic, there's the concept of a data set, which is in our case, if we think of a labeled data set where you have samples here will be the samples X, with I being the index of that sample. So if I have a data set of size N, so I is that index from the, let's say, 1 to N. With the label Y, and if you remember, it could be regression, it could be binary classification, it could be multi-class or multi-label. And usually data sets will be often have a training set and then a test set. Rule number one, and that's why it's so great in the current world that we have all these challenges, grand challenges, because one thing is you should never touch your test set. That's kind of rule number one. And really you should do all of your work and training and exploration should be only on the training set. And you should not touch the test sets, and only at the end go and evaluate there. We'll talk about like what to do if you don't have the test set available. We'll talk about it in a second. But yeah, training set and test set. And if you ask yourself, like, what is machine learning? At the core, one of the core aspects of machine learning is generalization. What can I learn from training that is able to learn? What concept can I learn that allows us to generalize it? And while you can formulate in different ways here, I'm putting it in the what's called supervised learning way, but the general aspect of learning and generalization, that's core to machine learning and AI these days. So what's the simplest possible classifier, I believe? What is a simpler one? Think for a second, what's the simplest one? I was not able to upload the quizzes on time. I know I would have done a survey for you at this point, but think about what's the simplest. I believe one of the simplest is the nearest neighbor. And you will sometimes hear the term non-parametric model. So non-parametric model, if you hear this, it may be a little bit confusing as a term you're like, oh, but think right away nearest neighbor as the simplest of the, and very powerful. It's very healthy in any task you do to always run nearest neighbor. You will be surprised how often nearest neighbor perform well. And the nearest neighbor will be done only on the training set. So at test time, you will do and look at nearest neighbor, nearest, and you will need a similarity function for that. But yeah, so nearest neighbor is probably the simplest one. So if you have a task like, is it a traffic light, a dog, or basketball, kayak, that nearest neighbor is the simplest one. And so to go ahead into this, yeah, so the nearest neighbor is a non-parametric. It lets the data speak for itself, predict the new cases based on your training set. So what's really great about the nearest neighbor is that training time, the complexity is really simple, is 01. I mean, it's like you just need to, in a sense, you have your data, that's it. But at test time, what is the complexity, you think? And the simplest version of nearest neighbor will be O of n. There's some way of optimizing it, but the simplest one. But what is the key of nearest neighbor is distance metric. And we'll come back later on distance metric because it's a very important aspect. For example, when we talk about kernels with SVM and support vector machine and other extension like this kernels, you can even look at transformers and self-attention models as a kernel machines. Like the key aspect of it is what is that distance? Because if you have two samples and you want to do, you have in your training set like 1,000 of images and you have your test set. So you have 1,000 of images for training and you test it, but what is the nearest neighbor What's the distance? And the simplest one will be something like a distance like a Manhattan or Euclidean distance will be the simplest one. And they're good to try. We'll discuss a few more as we go along, but just to give you a simple one, this is probably the simplest one, the one that you've seen early on when you did any kind of algebra, the Euclidean distance between this. What is the representation of an image here when I put xi, just a little thing? Yeah, this is just a long vector for now, okay? Just imagine a long vector. So you have a long vector here, and you have a long vector here, and you just do the Euclidean distance here, because you take that 2D matrix and just put it here. So in practice, you will do a little bit more, but this is the idea. So which distance metric to use? Aha, which distance metric to use? And I am asking this question because I want to talk about hyperparameters, or what's sometimes called model selection. Like, I don't know the answer. Maybe I have domain knowledge, and in this domain, I know that this distance metric works. But in some others, I may not have that knowledge. And for that, if I don't have that knowledge, it's a parameter that my model will not learn directly. It's a choice I need to make. It's a design choice I need to make. Really, very often, you will simply decide to make it as a hyperparameter, or you will have two models. If you could see it as model selection as well, two models, one for L1 or one for L2, or you call the distance, the type of distance metric, as a hyperparameter. So another question is like, how big if it's k nearest neighbor, where what I do is not just pick the nearest neighbor, but pick the two nearest neighbor or three nearest neighbors, and maybe do a majority vote out of it. The question is like, what is k nearest neighbor? And that's another example of hyperparameters. And I want to emphasize this because if there's one thing true with deep neural architectures, is that there are many of these hyperparameters. And you will see plenty of papers where the hyperparameters are selected almost by hand, and just a long list, and they say, oh, this is the architecture. We use 1,000 neurons in the first layers. We decided to use activation, this type of activation function, ReLU or some others, and we decided to have that many layers. And there's all these decisions to be made, and at the end of the day, they just pick some, maybe because of prior work that had selected it. There's some beautiful work that's done these days, even using reinforcement learning to select it. But if you have very few of these hyperparameters, the way to approach it is to take your training data set, and slice it in two. Okay, you take your training data set and slice it in two. You slice it so that you have your training data, and usually the validation set, if in the perfect world, you like your validation set to be maybe about the same size as your test set. If you can afford it, that will be great. And so what you will do is train multiple models, maybe one for k equal 1, k equal 2, k equal 3, or maybe for multiple distance matrix for L1 or L2. And then for each of them, we'll start looking at the validation data and just simply look which of these works better. So this is the basic. You've probably done that before. I will say for this class, you may not always be able to try all possible hyperparameters, but for a paper, if you decide to take your work and submit to a conference, I highly suggest to go and take the time to do all this. For the class, you have limited GPUs, and so we are not going to be picky about the hyperparameters as much, but that's something to be aware for, definitely for a paper. And I want to share like the methodology. For most of you, you hopefully will be lucky, and your data set already have a specified test set, specified validation set, and a training set. And so this is great because if you have a lot of data, this is the way to go. It's nice because then people can easily replicate your results. If you want to be very adventurous, then you can go ahead and make this a test set, like separate from a challenge. But for some of you, maybe in effective computing data sets and others, you may have not enough data. And what you will do is then, instead of have a dedicated test set, you just take your whole data set, take maybe 1/10 of the data set, call it the test set, and use 9/10 as training and validation, do all of your process, and then repeat it 10 times. And the extreme version would be leave one out, like leave one person out or one video out. Okay, I want to emphasize one thing here is that like linear classifier, I will again go a little bit faster on this, but what I want to talk here is the idea of, because this is just an introduction to neural network. I could have called this just neural network these days, but I don't know. For me, it's a linear classifier. A neuron is a lot like a linear classifier, so with a simple nonlinearity activation at the end. But at the core of a neuron, the core part is really a linear classifier. You could imagine when I'm asking myself, like, is it a dog or not? I could imagine take that whole image, make it a vector, and then use only one neuron. I know that's quite crazy, but yeah, imagine that's called one neuron. By the way, one neuron is called a linear classifier. Okay, depending on which activation function, it will be maybe slightly different from a linear classifier, but it will be in the same family. And what are the three main parts of almost any classifier, but specifically linear classifiers and neural networks? Three tasks when you think about learning classifier. One is defining your score function, and we'll discuss that in a minute. And for a lot of neural networks, because you select specific type of neurons, and then you kind of bypassing that design question. But I'd like you to at least be aware that underneath there is that happening. The one that is important for almost any model is the loss function. You need to define what are you penalizing, what is it that you're penalizing, what kind of situation you want to penalize. And then you need to go from maybe a model that you initialize randomly, in this case maybe this one neuron that you have, and it has a bunch of weights, and you may be initializing randomly. You want to start from that random position in the space of your model, parameter space, to get to that, hopefully, to that global optima that really gives you the best possible classification. And that's called optimization, that walking through the space. And I think the intuition of walking is really good in this case. So the score function, this is something that is happening in any neural network, but we don't realize it, and I want you to take at least a moment to think about it. When you have the image and then you have all these class labels, the score function is, what it answers is, what should be the prediction score for each class label, okay? So if you have, for example, you have the image, and it has the possibility of a dog, it has a possibility of a cat, a dog, a pig. The idea here is I want to have a score for each of these labels. And the way to do it will be, maybe the simplest one would be to have one neuron, and in this naming will be one classifier, linear classifier, for each of them. You'll have one neuron for duck, one neuron for cat, one neuron for dog, and one for pig and bird. And a neuron at its simplest, a linear with a linear activation function, a neuron with a linear activation is this exact function. And so X, as you remember, is a vector usually. And I say WI because if it's a training set, I may have many of these images. And then you have W, which is the same W or the weight for all my samples. That's what I'm trying to learn. And I'm also trying to learn the bias as well. And we will explain visually what the bias can be interpreted as well. But these are the two sets of parameters that I will learn. And what this function is this one value that tells you how much is it, how do you score. So you could score it for a duck, score it for a cat, score it for a dog, for each of them. I want to give an example with numbers. So if it is 3072, because it's an image of 32 by 32 by 3, this is a very long vector, then the weight will be, let's say that I have 10 of these classes, then it's going to be 10 times 3072. I have only a bias for each class, or only one bias per class, and these are going to be my parameters together. Okay, so this is the idea for the, and the number of class is the number of scores will be the number of classes. And so the W, what it does is give you the direction of the slope of the linear classification, and the beta. The bias is there to give you the distance to it. So the distance, and then the W gives you the slope. So this is just basic linear classifier. You've seen it many times. I just want to help you with like naming convention, because it gets very confusing. You rarely see nicely written like this. In fact, most of the time, if you're lucky, you will get to this, which what it means is that you took your bias and in fact added it just simply by making your input slightly longer by only adding 1 to it, and now you have all your parameters in one W. It's just cleaner. And so another nice thing you can do is, because you will have many classifiers, really you will have many sets of parameters. You will have one set of parameters for dog, for cat, for all of them. You could simply say I have a different function, or you could go very simple, very tight. And so these are all different ways of naming. These are all equivalent. This is just a notation. So I would love it if you always take the time to say, hey, what are my parameters? But a lot of time people will just take and maybe they will add here a simple thing, like they may take the time to have an X here, but that's maybe the only thing. But this is equivalent to this one as well. So if you have many classes, then you have many of these linear classifiers. In this case, what I show here is 3 neurons, 3 linear with linear activation. This is what you see here. But how do you get to optimization? If you want to optimize this, you have, let's say, 10 of these scores. But then I need to ask myself, now I have 10 of these scores given an image during training. I have 10 of these scores, and let's say I have 1,000 images. And let's say the real label is dog. And so I want, and the scores right now, dog is high, cat is also quite high. And I want to congratulate my current weights to say, hey, you got it, perfect. Or maybe if it was the opposite and let's say dog was selected too high, I would like to say, no, this is not correct. How can I go ahead and tell the algorithm this is not the right thing or this is the right thing? The loss function, in very simple term, is how to assign only one number represented how unhappy we are about these scores. Okay, so you get many different scores for each possible class, And then you have to ask yourself, like, how do I finally at the end of the day just give one number? And so, and that's what the almost science of loss function comes in. And it's almost a science in itself to looking and deciding what loss function to use. So the loss function quantifies the amount by which the prediction score deviates from the actual values. That is what the key aspect is. So here, because these scores are very different, and I want to have a loss, maybe a loss that goes always from 0 to 1, how can I take all these scores and normalize it? And so there's very different ways, but probably the simplest one is using a logistic. I go from numbers that goes from minus infinity, and I want to normalize it from 0 to 1 or minus 1 to 1. What is the simplest function to that? This is a logistic function. It goes from minus infinity to plus infinity, and it can nicely give you a number from 0 to 1. So now I can take all of these scores and simply put them together. So this is the scores here, and if I have only one score and I want to normalize it, then I can use that logistic function in this case. If you have two of them, it's also quite simple because one is the opposite. Suppose that it's either a dog, or all your images are either dog or cat, or it's dog or no dog, for example. In this case, then it becomes a simple logistic regression, but this is the same equation. And so in this case, the true class in a logistic regression, like the 0 is seen as your decision boundary in this case. And this is what you see here. But if you have multiple class, then you just have a very nice, and now people use that like term softmax, not realizing what it does, but softmax, what it does, it's just a normalization. It just brings everything that could go from minus infinity to plus infinity to something between 0 and 1. And now, are there any parameters that are learned just in that? No, the loss function itself doesn't have parameters in it. The parameters are before the loss function. And we'll look at it in the neural network. But when you say I have a softmax layer in a neural network, softmax doesn't have parameters. It's just a normalization. So softmax is just there, and the softmax, what it does is just allows you to easily implement some other loss function. So now what I did with this softmax is I ended up taking all of my 10 different scores and normalizing them. So I get a vector instead of 10, but I can go ahead and normalize it. And once it's normalized, then you can look at the cross entropy. That softmax is there. And then you can look at this and take advantage. And then you minimize, in the case of a cross entropy, minimizing the negative log likelihood of it. And this is just a matrix version of that, that as an example of that, that you can look more in details in the slides, where you have your weights, you have your input and your beta, and you can see the different steps of it. One is you take the exponential of this, and then you go ahead and you can normalize this, and that's finally what gives you the log on that. So, okay. This is one example of loss. I just want to give another one, and I know we're running a little bit out of time, so I'm going to wrap up relatively soon. But the other one, which is under many, many names, but I like it quite a bit, is the hinge loss, and it definitely has been used and is used quite a bit these days in many different approaches. We'll discuss more in a little bit, but here the idea is not just to look at the distance. It's not just normalizing and looking at the peak in this, In this case, what you will do is look at the difference between the correct class and the incorrect class. And the trick here is that because you sum over all the incorrect labels, really what you end up doing is like you end up penalizing mistakes. You ended up penalizing mistakes, and that's a trick because of the max. So what you want is, if it's correct, it's good. There's nothing here. I'm not, although you could change it, but it's okay. But if it's wrong, like how wrong is it? And how wrong is it will be that margin that you want, and you would like that margin to be as large as possible. And one of the most famous use of that, at least it was famous back in the days, was support vector machines. Contrastive learning has a flavor of that as well. There is one little kind of hyperparameters, but this one often doesn't matter as much. But it's this delta to allow you to get a bond, some kind of buffer into this. So these are two losses. There will be more during the class. I just wanted, but a loss in general has three main parts, okay, to it. One is the data part. This is the main thing we discuss about. The data part, the data term. How much is my data matching my expectations? That's kind of the loss that I talked to you about. And we talk about different versions of that. But there's also two different components to that can be added. One is regularization. Regularization is often there to prevent the model to becoming too complex. You will often add this regularization. This is in almost every model that you would get some level of regularization, primarily because in the perfect world, you will have infinite amount of data, and probably you could be a lot simpler in your regularization. But a lot of time you have example that may not have never been in the test set, and so you want to be able to generalize to them, and at the same time keeping the complexity of your model simpler. So it's either for smoothness, so there's very interesting. And the lambda, you ask yourself, it is a hyperparameter. That's another example of these hyperparameters. And there's something that we'll discuss a little bit later. Sometimes you will also have in your optimization some constraints. You don't want certain parameters to go larger than a certain threshold. You will have some constraints. This is not often, but it does. Why is it not so often? It becomes a problem for optimization. Like the more constraints you have, the optimization becomes more complex. Often for the regularization these days, people have managed to find very interesting ways of regularizing and still being able to get a gradient. Sometimes with the constraints, you get some nonlinearity or some other things that makes a typical gradient-based optimization a lot more challenging. So we'll discuss more on Thursday, the core of this, which is on the neural network, where at the end, I'm just going to give you 1 or 2 slides, and we'll discuss more, a few slides, but we'll discuss more on Thursday, just a teaser. But neurons, what they are linear classifiers. And that's really the core of it. You see exactly the same linear classifier. So a neuron is a linear classifier, but there's an activation function to know like how, and the activation allows you to almost, some of them almost look like a on-off switch. And so what's great is that it allows you to say, and that's part of how the neurons will go, gather a bunch of evidence. You could imagine gather a bunch of evidence, and then once you have enough evidence, then you activate, you pass that threshold. Now we use neurons, and a lot of these neurons don't even look like neurons, or at least nowhere close to what human neurons are. But at the basic, these were kind of a linear classifier with an activation function. You will, when we think of neural network, the simplest one, the multi-layer perceptron, each of these arrow, not each arrow, but if you set all of these arrows together, this is one neuron. So take all of these evidences from all of them and get one neuron and output from one neuron. That's, you could say, output of a neuron, response of a neuron. That sometimes you could call them scores, but the scores will usually only be used at the end when you talk about scores. You here have 3 scores. No, sorry, 4 scores maybe. Oh no, sorry, you have only 1 score. You have only 1 neuron at the end. But if you had many of these neurons, so here it's only dog or not. But if you had dog, cats, and something, you could have many of these at the end. So these will be scores. But here we'll talk about response or at the output of that. And so the building block of this is simply that linear classifier plus this activation function. And as you know, there's many of these activation functions. We, back in the days, were focusing primarily on these 2, tanh and sigmoid. In fact, LSTM, which used to be very popular, long short-term memory, LSTM, which is a type of recurrent neural network. And what was really interesting is that, and we'll look at it when we look at the recurrent neural network, is tanh, the main thing was it nicely goes from -1 to 1, while the sigmoid goes from 0 to 1. And when you're building or designing these architectures, you may realize that having a positive and negative may help your learning. And so you will decide from a design perspective. So, and so multi-layer neural network simply is a recursive process. It's like, you could see it, you have 1 layer of neurons. So 1 neuron, 2 neurons, 3 neurons, 4 neurons. This is 1 layer, and that's what I show here. And so for this layer, I will learn a set of weights. What is it? Is I will learn a set of weight for neuron 1, a set of weight for neuron 2, set of weight on neuron 3. And so W is often seen almost as a matrix, or what's called also a 3D or 4D matrix, what's called a tensor. So this, when you hear the word tensor, you can do multidimensional matrix as one way to think of a tensor. So when I say W here, are all these neural parameters from the neural network. And so I have parameters for the first layer, parameters for a second layer, parameters for the third layers. And then here I could have many scores. In this kind I have only 1 output. So the score function here, the output here, what it is just it's just recurrence. Like it's just like from one out, and then the output of the one goes in the output of the other, and the output of the third one. And our loss function is over that output. So output here is only 1, and here if you have an Euclidean loss, all this. And loss, as you remember, is only one number that tells you how good or bad things. And so I'm gonna, I think this, yeah, this was my last sentence, last slide. When you do these, there is 2 terms I want you to one is inference. Inference, what it means is like feed forward, like moving through the network, like inference. Like inference is like I have X and I get my inference Y or my scores. So inference is use the score, or inference is both get the score and use them. And at that point, when you do inference, it should say use, compute the score here, and it should not say use, compute the scores and use them. And that takes already learned parameters. And then at training, the training time is, that's where you use the loss function, and then you do optimization. And one way of doing optimization is gradient-based approach. And when you do this gradient-based approach, one thing you will realize is internally, you will do inference internally in that loop of optimization. You will often do some inference, but what you will do is for a specific set W at that time, at that iteration. So we'll discuss more there. So don't forget to do today your project preference form. That's everybody, all students. Tomorrow, also select in your reading group, just be sure to select your Google, go in your Google Sheet, your own study group, and select. Post your summary on Friday or before that. It's even better if you do before. Oh, I forgot to put on Thursday morning, be sure to have your highlights form. And then on Monday, do the discussion. So yeah, thank you very much for your attention.